Have you ever encountered a mathematical puzzle that seems to go on forever? Today, we're going to unravel the mystery of an infinite nested radical. Specifically, we'll find the value of this beauty, the square root of 43 plus the square root of 43 minus the square root of 43 plus. Well, you get the idea. This pattern continues infinitely, and surprisingly, it converges to a single value. Let's discover what that value is and prove it step by step. These types of nested expressions appear frequently in mathematical competitions and advanced calculus, so mastering the approach will give you powerful problem-solving tools. We'll use a technique called recursive system stability to tackle this head-on. First, let's turn our infinite expression into something we can work with mathematically. Instead of trying to handle the entire infinite expression at once, we'll define a recursive sequence that models our nested radical. We'll start with some initial value, let's say the square root of 43, and then define each subsequent term by applying our nested radical pattern. Each term gets us one step closer to the final value of our infinite expression. So if we call our function f of x, it equals the square root of 43 plus the square root of 43 minus x. This elegantly captures the pattern of our nested radical. Before we find the exact value, we need to establish that our sequence won't shoot off to infinity. Let's prove that all terms stay within a reasonable range, specifically between 6 and 8. Starting with our initial value, the square root of 43 is approximately 6.557, which is indeed between 6 and 8. Now, let's assume any term in our sequence is between 6 and 8. What about the next term? If we substitute these bounds, we can show that the next term also stays within this range. For the lower bound, even when x is at its maximum of 8, the result is still greater than 6. And for the upper bound, even when x is at its minimum of 6, the result stays below 8. This confirms that our sequence remains bounded, which is crucial for convergence. Now for the mathematical magic. We'll use the contraction mapping principle, which tells us that if a function pulls points closer together each time it's applied, it eventually converges to a fixed point. To verify this property, we need to find the derivative of our function. After some calculus work, we get this expression for f prime of x. When we analyze this derivative over our range from 6 to 8, we find something remarkable. The absolute value of the derivative is always less than 1 over 168, which is much smaller than 1. This is exactly what we wanted. Since the derivative's absolute value is less than 1, our function is what mathematicians call a contraction mapping. This guarantees convergence to a unique fixed point. We've now verified all the conditions of the Banach fixed point theorem. This powerful theorem tells us that not only does a unique solution exist within our range, but also that our sequence will converge to this value regardless of our starting point. What's especially elegant about this approach is that we've proven convergence before even calculating the actual value. We know with mathematical certainty that our nested radical equals a specific number, we just need to find it. We've already seen how the structure of this nested radical lets us define a pair of variables. Let's go further and find the exact value. We start by setting the entire expression equal to. Looking at the inner part of the radical, we define that substructure as m. So now, we can rewrite the equation as east equals the square root of 43 plus m. Squaring both sides, we get e squared equals 43 plus m. Let's keep this result highlighted, we'll need it later. Now, let's isolate the structure we called m earlier. Again, we define the inner expression, this time in terms of e. This gives us m equals the square root of 43 minus e. Squaring again, we now get m squared equals 43 minus e. We'll also save this second equation. Now we're ready to connect them. We place both equations together so we can compare and subtract them directly. Subtracting one from the other eliminates the constants. We get e squared minus m squared equals e plus m. Recognize this identity? It's a difference of squares, so it factors to e minus m times e plus m equals e plus m. And now, we can cancel the common term on both sides. This simplifies to a very clean result. E minus m equals 1. So we isolate m and find that m equals e minus 1. Now we substitute this back into our earlier equation. E squared equals 43 plus E minus 1. Simplifying, this becomes E squared equals E plus 42, and then E squared minus E minus 42 equals 0. Solving this quadratic equation, we find two possible solutions, E equals 7 or E equals negative 6. But since all our terms are positive, the only meaningful solution is E equals 7, the exact value of our infinite nested radical. Let's double-check our answer by examining the stability at this fixed point. The derivative of our function at equals 7 is negative 1 over 168, which has an absolute value less than 1. This confirms that our fixed point is stable, that we've proven rigorously that our infinite nested radical converges to exactly 7. Isn't it amazing that such a complex-looking expression simplifies to a simple integer? The methods we've used today, recursive sequences, the contraction mapping principle, and fixed point theory, are powerful tools that apply to many areas of mathematics and even computer science algorithms. Next time you encounter an infinite pattern, remember, with the right approach, infinity can sometimes be tamed into something beautifully simple.